All right. So today, hopefully, we have swivel back. Do we have swivel? We had swivel back a moment ago. Yes, we have swivel back. We're going to continue with our quest towards equidistribution. So we did denseness. And we did denseness of n alpha. We could prove denseness of n squared alpha, n cubed alpha, n to the fourth alpha. Why are we not going to prove that? Any thoughts? Well, does it follow immediately from the denseness of n alpha? If you know n alpha is dense, do you know that when you progress along the squares?
No, because I feel like if there are no repeating patterns, or if the repetition fizzles out amongst single multiples, then
See, there's a difference between what is true and what you can easily prove using the same methods. So in the book, I go through a proof, I think, of the denseness of n squared alpha, assuming that alpha is well approximable by rationals up to a certain order. And then the purpose of that proof is to give you a sense of how you can use knowledge of how well approximable a number is to get and glean information. The other thing is, we have easy proofs of equidistribution of n to the k alpha. And if you can prove n to the k alpha is equidistributed, you get denseness of n to the k alpha directly. But these do require a little bit more machinery. They're going to require what type of machinery? If it was a little question, you'd say induction, because that's basically all we've been doing. But in this class, what have we been doing every time? What's the key techniques we've learned? What do we start the course doing? What's subject matter? Fourier. So we're going to use Fourier series. So the question is, why do we want to use Fourier series? Well, a lot of times we're looking at things, so we're doing equidistribution. Okay, so we have alpha is not rational, and we study an alpha mod 1. We'll call that xn. As soon as you see the mod 1, why is Fourier analysis a good thing to think about? What makes us happy? Yes? So it's periodic on 0, 1. But what in particular makes us happy when we see this? Why is Fourier analysis going to be such a great fit? Good. If we differ by an integer, when we raise it to, when we look at e to the 2 pi I times an integer, it's always 1. So we can drop the mod 1 condition. Most of the time, when you are doing difficult and analytic arguments, you cannot just drop part of the expression without any harm happening. This is one of the few times you can, and this is the key why we want to do Fourier analysis. So e to the 2 pi I xn is e to the 2 pi I n alpha. That's really nice. There's another great way to look at e to the 2 pi I n alpha. So I need to use some laws of exponents. I can write this as e to the 2 pi I alpha raised to the nth power. So that basically I have a geometric progression. I'll be dancing around the circle, and every time I'm going to be moving by the same angle. Okay? So this is why, if you were to take a class with Professor Silva, or for those of you at home at another institution with whoever your local ergodic theorist is, they would phrase this a little bit differently. But it's the same idea. Okay? You need a little bit of a dictionary times to translate between my talk in regular English, between analysis and ergodic theory. But essentially what's going on here is we're moving a constant angle around. And as long as that angle is irrational, we're going to fill everything. All right, so now let's keep thinking a little bit more about what's going on. What could be dangerous for us? What kind of alpha will be bad? So when we're going over here, if we're trying to get equidistribution, which alpha do we need to stay away from if we want equidistribution? Rationals. If alpha is 1/5, we're only going to take on 5 different values here. Well, let's think about what goes on here. If alpha is 1/5, we have e to the 2 pi I over 5. We're only going to get 5 different values here. And we're going to just keep hitting the same points on the circle. And so again, the idea is as long as alpha is irrational, we will be fine. All right, so we're going to introduce something called the characteristic function. Chi AB of x is going to be 1 if x is in AB, which of course lives in 0, 1. I mean, where else could you live? And 0 otherwise. So what we need to do is we need to prove for all AB contained in 0, 1, the limit as n goes to infinity of 1 over n sum n goes from, let's see, I'll do 0 to n, well, I guess 1 to n, of chi AB of xn. What should that equal? If we're equidistributed, what should that equal? B minus a. And then there's a couple of different tweaks we could do. Here I'm starting at n equals 1. Could do n equals 0. And then we just shift things a little bit. And then sometimes we actually want to go from minus n to n. And so for this problem, I think we like to do that as well. Yeah. Could do n goes from minus n to n, divide by 2n plus 1. For a lot of problems, it's not going to make too much of a difference. Clearly, including the point n equals 0, that's fine. That's trivial. The other one requires a little bit more thought. If you know you're equidistributed, if you allow n to go from minus n to n, is that the same as you're equidistributed from n goes from 0 or 1 to n? And the answer could depend on the sequence. For the sequence we're looking here, our sequence is really nice. And in fact, we know, there's really nice relationships between xn and x minus n. So you should think about whether or not, for this special case, it matters. Or more generally, can I give you a pathological sequence which is equidistributed from minus n to n, but not from 0 to n? Or do you want to just do that right now and just knock it out of the park? So, and I'll use a different letter. Could an, so in honor of Amherst, some kind of pathologically bad example, be equidistributed from minus n to n as n goes to infinity, but not from 1 to n. So what do you think? And now again, I'm not assuming right now that xn is of the form n alpha mod 1. You can choose it freely. Do you think you can choose it in such a way that you lose equidistribution?
I mean, we're not allowed to. There has to be like some consistency to this sequence.
No, it's Amherst. It's inconsistent.
So we could just say, let it equal a series like that for. Oh, I see.
Yes.
But could you say like it equals all of the irrationals on minus n to n, and then like except for some like a minus 0.5 or something? Some like rational number that's like less than 0.
Not quite. I need it to be equidistributed as I go from minus n to n. So you have to explicitly give me formulas. It might help if instead of looking at the interval like this, would it help you if I wrote the interval like this? Because if I can just shift things like this, shift happens, this isn't bad. Look at it like this. Where do you want the xn's to live if n is positive?
some subset, some proper subset of the interval.
Right, so which subset do you want the xn's to live with if n is positive? Where should we have them all live? 0 to 1/2. Excellent. So maybe xn is n alpha mod 1 divided by 2 if n is greater than 0. That's going to be equidistributed here. What should I do for the negatives? Same thing, right. So now xn is equal to n alpha mod 1 over 2 if n is negative. And so now things are not quite as they should be. It's not the same as n alpha mod 1. And now if I do this, each one of these sequences is equidistributed. They'll fill in here exactly as they should. But if I only restrict to the positives, I'm going to have some problems. So it's really important when you have problems like this that you think, does it matter how you count? This is a huge issue in how you go through things. I was at a conference just this past weekend, and one of the talks was describing how you could count things this way, or this way, or this way, and fortunately we get the same answer no matter which way you count. But for some problems, that's not the case. You've got to be very careful how you go off to infinity. Let me belabor the point. I think I can. Let's consider the integral from minus infinity to infinity of x times 1 over pi 1 over 1 plus x squared dx. So at least 2 people in the class should tell me what integral I'm looking at. So what is the interpretation of this integral? Well, it would be arctan if I didn't have the x. What does this integral represent? Actually, at least 3 people should.
The expected value of an arctan.
The expected value, not of the arctan, the expected value of what distribution? I'll start looking at people who should know. At least one person has written a paper on this. And I know 2 others had it in a class. This makes me feel so good as a professor. What distribution? The Cauchy. Right? This is the density of the Cauchy. It integrates to 1. This is calculating the expected value. What's the expected value of the Cauchy? If you look at this, I have a symmetric function for my density. I multiply by x. I get an odd function. What's the integral of an odd function? 0. The problem is, if I put in absolute values, the integral diverges. So in order for an integral like this to exist, what we often want to be true is we want the limit as a and b go to infinity, however the hell they want, the integral from minus a to b, it's a technical term, x 1 over pi 1 over 1 plus x squared dx. And that should exist, and the answer should be independent of how a and b go to infinity. So a really good choice is, let's take b to be, I was going to say, let's do it a little bit more generally, n times a. Yeah, we'll do it this way. We'll do it n times a. And then in that case, we'll get the limit as a goes to infinity of the integral from minus a to n times a of x 1 over pi 1 over 1 plus x squared dx. Well, the integral from minus a to a is 0. So this then becomes the same as I can integrate from a to na. The integrand is approximately x over 1 plus x squared. If a is big, it's approximately 1 over x. So the integral of 1 over x is natural log. So this is approximately 1 over pi, the natural log of na minus the natural log of a, which is the natural log of n divided by pi. And so the answer depends on how we go to infinity. This is very similar to what we're getting over here when we look at our sequence. It's depending how we have the terms, how we take the terms. So there's a lot of great stuff in analysis on the dangers of this. We may have talked about the rearrangement theorem early in the semester, where if you have a sequence that converges conditionally but not absolutely, you can rearrange the terms however you want. And if you do that, you can actually make it so that the lim sup is whatever you want and the lim inf is whatever you want. So this is all just to warn you about the dangers of calculations like this. Okay, any questions about this?
Could you also show something like that that depends on how you go to infinity by differentiating with respect to A?
Of the bounds of integration?
Yeah, I'm just showing that for, well,
I'm not convinced on that, because it looks like it's going to be 0 at those endpoints. If you maybe differentiate with respect to little n, that might be different. Okay, so we will consider sequences, of the form n times alpha. So for us, there's a really nice symmetry. If one side is equidistributed, the other side will be equidistributed. We're going to consider this step function. That's what we want. We want to show no matter what interval a, b you take, this converges to b minus a. The problem is sharp cutoff functions are bad. They're not easy to work with. So sharp cutoffs are bad. So this is a general principle. This is a value judgment. Sharp cutoffs are not good. The problem is we live in a world that exists and is built upon sharp cutoffs. Out of curiosity, how many people here got into Williams College?
off the waiting list.
So that's an example, I guess, of a cutoff, but eventually it did become sharp.
Eventually.
How many people had like 90% of themselves accepted by Williams? You're allowed to take classes from the following departments, but you are excluded from this, and you can't play on these sports, and you can't participate in these activities. And you're not allowed to live in the good dorm. Yeah. We don't really believe in something like that. If we accept you, we accept you. We provide resources, we provide financial aid, we provide textbooks, and we provide what you need. We try to treat all the students equally. We don't accept 90% of a student, right? We are committed to accepting the entire person. It's much easier to count physically like this. We're not going to have a huge number of people where this person is taking 3 classes this semester, this person is taking 2 classes, this person is taking 4 classes because they're a full student, this person, we're counting them 120%, they're taking 6 classes. We're not doing something like that. Let's look at things on the mathematical side. How many primes are there up to x? Well, we just count all the primes, and you count the primes equally. All the primes count the same. It turns out it's a lot easier, and we'll see this when we get to L functions, to put weights on the primes. For a lot of things similar to putting weights, you don't stop abruptly. And if you want, you can think of this as putting in weights on the numbers just past what you care about. So if I care about the interval AB, and here's 1, and here's 0. If I have sharp cutoffs like this, it's very hard for me to work with a discontinuous function. I lose a lot of theorems if my function is not continuous. So I want to study continuous functions. Well, the problem is if I study continuous functions, I can't instantaneously get from 1 down to 0. So what can I do?
You can either restrict the functions to be periodic or to FA equals FB, or you can try to extend it to the whole unit integral, making.
Well, I basically only give about what's going on between A and B, but I want to be continuous. So I realize I'm not being consistent. I realize I want 2 things that I cannot have at the same time, so I'm going to have to compromise. And I have determined that, to me, I care far more about continuity than I care about just being between A and B. But that said, I really, really, really don't care about things outside of AB. And so I know I have to do them a little bit, but.
Draw a line connecting the endpoints to A minus epsilon and B plus epsilon.
Excellent. And is epsilon big or small? Small. Right? Choose a really small epsilon so you're crunching down very fast. And so we drop down, chrump, chrump. We drop down like this. and then we put ourselves to be 0. And so now we've modified our step function. It's now continuous. Unfortunately, what property have we lost? So it's no longer just between a and b, but if we choose epsilon sufficiently small, hopefully that's not going to be that bad. And for each epsilon, we can do something like this, and then we can have a sequence of functions that are all continuous. But unfortunately, they're only continuous. What other property would you like to have? It would be nice to have differentiable. Now, fortunately, if we look at what's going on here, they're actually they're Lipschitz with exponent 1. So even though it's not differentiable, the left and the right-hand limits exist at all these places. And that's all we needed for Dirichlet's theorem. Or we could tweak our function and have our function be continuous and differentiable at these places by just being a little bit more careful. You could even have it decay fast. We could have some kind of like exponential decay if we wanted. Lots of things we could do. A really good function to look at that we won't is e to the negative 1 over x minus a 1 over b minus x. Let's see if I did this right. Good. And and then we'll have the function be 0 otherwise. So of course, when I do otherwise, I should really do what comes first. So where am I defining this function to be this? For what values of x?
A minus epsilon.
Nope. Nope. The a minus epsilon is close, but epsilon is a fixed distance. I want to just go from a less than x less than b. Let's see what happens. If I have x approaching b from below, this is going to be a really small positive number. This is going to be a fixed positive number, 1 over b minus a. So if x is approaching b, let's say x is equal to b minus 1 over n. Then this looks like 1 over n becomes an n upstairs. We have an e to the negative n times a constant. What does that look like? I'm sorry? Damn small. Right. It's really going to be small as x approaches b from below. Similarly, as x approaches a from above, I'll write x as a plus 1 over n. I'm going to get a 1 over n in the denominator here. The n comes upstairs. So this function is going to have incredible decay near a and b. And so I can do something like this to match however much vanishing I want at the point. So if I really want to have lots of continuity, there are ways to do this. If you continue an analysis, you need to learn how to deal with special functions like this. Okay? So again, there's a lot of algebra in the chapter. I want to try to highlight the ideas behind why we're doing that algebra and leave the algebra for you to read. So looking at what's going on, what we can do is we can replace our discontinuous characteristic function with continuous functions. This one overshoots. Sometimes rather than overshooting, you might want to undershoot and drop and land just a little bit before a and b. So in the book, I think I call them a1 of j and a2 of j. I forget which one is the larger one, if it's a1 or a2. Okay, a1 is the smaller one. So a1, now of course the camera's still looking at the notes. Come camera. All right, so it's there. All right. So now over here we would have a1j of x, a2j of x, and I'll just draw it over here. Here's a, here's b, here's a plus 1 over j, here's b minus 1 over j. And then the other one is here's a minus 1 over j, here's b plus 1 over j. And actually, I think the way I want to do this. So it'll be 1 from a plus 1 over j all the way up to b minus 1 over j, and then it'll drop off very quickly to a and very quickly to b. All right. So now when we're doing something like this, we have our test functions. They're continuous. we have a bunch of theorems at our disposal. What theorems do we have at our disposal now? Poisson summation? We
For the limit on the other board.
We do have Poisson summation, but it's not a bad idea to think of Poisson summation because we have over here a sum over n. But we're actually not going to use Poisson summation for once. So what else could we use instead of Poisson summation? We have continuous functions on 0, 1. What other theorems do we have? We have Fayet's theorem. We also have Dirichlet's theorem. So we could use Dirichlet's theorem and use the pure Fourier coefficients, or we could use Fayet's theorem, which has better convergence if we were willing to introduce a little bit of weights.
I think you need differentiability for.
We don't need differentiability if we just need Lipschitz. So as long as the left and right derivatives exist, we're fine. So what do you think? Should we use Fayet's theorem and not worry about the fact that we're putting in some weights and just use the thing that's easier? Or should we say, oh, I don't really like weights, let's use Dirichlet's theorem? What have we just introduced? We've just introduced weights, essentially. Right? We're weighting all the numbers between a and b with 1, then all the numbers between a and a minus 1 over j, we have a very quickly decreasing weight, and then we weight by 0 elsewhere. So we've already put in weights. You know, in for a penny, right? At this point, why not use Fayet? There's one other thing that's worth remarking here. What if a is such that a is 0? Then this is going to be wrapping around, and the way I've drawn the picture is not necessarily correct. It's a minor. You should make a little remark about that. If necessary, just translate the interval 0, 1. The only case that you might have to worry about is if a equals 0 and b equals 1. Well, I will leave that as an exercise to you. It is not too hard to show that the sum will converge to b minus a in that case. Okay? If you are not laughing, you should probably consider taking a different course. Okay? So that one's not going to be that bad of a problem. So we really, don't worry too much about stuff like this. So we have Fayet's theorem. So Fayet can uniformly approximate these functions, a1j and a2j with finite trig polynomials. Say negative m less than equal to m. Let's make it a clear lowercase m, less than equal to big M. I don't really care what those coefficients are. I just care that there are some coefficients. Do I have to have the same m for a1j and a2j? Or could they be different m's? What do you think? So I know Fayet tells me I've got a finite trig polynomial that approximates a1j. I have a finite trig polynomial that approximates a2j. I'm using 1 over j as my epsilon.
You can probably, it wouldn't matter. You just take the max of both of them since they converge to the form is.
Well, okay, but if we take the max of both of them, we might have added terms to one of them. We can't just add terms.
That's true. So there's,
But what could we do? We can't add terms if the coefficients are.
say again?
We can add terms if the coefficients are what?
0.
0. So in some sense, Fayet tells us we have a theorem. Fayet tells us we have an approximation that's within epsilon. And we might have a different m for each one. But what we can do is we can say, I don't need to use the trig polynomial from Fayet, for a given value of m. I just need a trig polynomial that's good. And Fayet is giving me two different candidates. And if one of them has a larger m than the other, then just add a couple more zeros. And just pad it out. So what might be happening is the trig polynomial we get where m goes from minus m to m may not be the one you would get from Fayet's theorem. But it will still be within epsilon. And that's all that matters. And this way you can use the same m for both of them. So again, there's a huge number of technical points that in the end, all of them can be surmounted. but you've got to get in the habit of dealing with stuff like this. And just thinking, I've got to be very careful. Now the other question is, well, what if I just take the larger m? If I add more terms in my phase series, does the approximation get worse?
No, that's the definition of, well, I was sort of about to ask, isn't the definition of approaching or converging to a, or to j that for each of the m's greater than each small m greater than big M?
So question, as m goes to infinity, does fm f of x monotonically improve in approximation to f? So as we take more and more terms, do we never do worse? What do you think? We have not proved that theorem. Does that seem like a reasonable theorem? That the more terms you add, the better. Now, unfortunately, as soon as you add new terms, you also change all the weights. And you change the weights by small amounts. It is not clear to me at all that adding more terms will make you do better at every single point. Maybe you do better on average. Maybe you do better in the sense of L2. But maybe by adding some more points, you get a little bit worse at one point, but that makes you much better in many other points. So overall, it's a good thing to do. Consider the following sequence. 1/2, 1/2, 1, 1/3, 1/3, 1/3, 1/2, 1/4, 1/4, 1/4, 1/4, 1/3. What should come next? Good. How many 1/5? And then what comes next? Okay. And now 6 1/6, and then a, oh, right. So this is a classic sequence. It's existed for almost 20 seconds now. Right? It's very well known. Yes. What can you tell me about this sequence? Converges to 0. Does it converge to 0 monotonically? No. And we could make it much worse than this. This is very mild bumps. Small little hiccups as you're going. It's not a huge change, but you get a little bit worse. And so we could have stuff like that. And so over here, we've got to be very careful. You can't just assume if you take more terms, the phase series is better. That might be a wonderful theorem to try to prove. And if you want to test your skills, say you have a function, assume whatever you want. Assume it's differentiable 3 or 4 times if you want, and just see, does the phase series uniformly get better at every single point? Or can you find a couple of instances where things change? A good example of another place where you might have seen something like this is, how many of you have seen the proof of Riemann sums converge to the area under the curve? This should be essentially who's a math major. If you have not seen a proof that the Riemann sums converge to the area under the curve, privately email me, and I will privately send you a link to a lecture to watch this. It's one of the things you need to do when you're getting the secret hand signal to let people know that you are a mathematician. How have you proved that Riemann sums converge? What do? You partition the interval. Here's 0, here's 1. And I partition 1 over n, 2 over n, 3 over n. What's my next partition? I'm sorry? Yeah. So this is my nth partition, and I get my lower sum ln, my upper sum un. Okay, so this is my partition with n. What's my next partition? So 2n is a much better choice for what do we often do in calculus classes. Right, and so we would go, no, so we do this with n equals 12, and then the next one we do would be n equals, I'm sorry, after n equals 12, what would we do next? 13. And so the next one, might be 0, 1 over n plus 1, 2 over n plus 1, ... Or the other way of going is 0, 1 over 2n, 2 over 2n. The advantage of this approach is that it's a refinement of this partition. And if you do this, then the lowest sum L2n is going to be greater than or equal to the lowest sum of Ln. The upper sum of L2n, the upper sum at 2n is going to be less than or equal to the upper sum at n. When you have a partition like this, is it possible that the lower sums and the upper sums are not monotonic? So again, that's a good extra credit problem. Show that if you have a partition like this, that maybe the lower sums are not monotonically increasing. Maybe the upper sums are not monotonically decreasing. However, as you get larger and larger and larger, they will decrease, they will converge to a common value, but not necessarily in the same direction.
I'm not sure, what is the definition of convergence that's at work here?
Well, the convergence is I have, for each value of n, I partition, I have my continuous function,
Right.
I calculate the lowest sum and the upper sum approximation, and then the limit as n goes to infinity, the lowest sum ln and the upper sum un converge to a common value.
Right.
And that common value is the area under the curve. But it's not saying that the lowest sums have to converge monotonically, always going up, never going down. It's not saying the upper sums always go down and never go up. I could locally go down a little bit. As I do a new partition, I might have things a little bit worse.
Now, I might just be recalling incorrectly.
Okay.
But I thought that the definition of convergence, say of a series,
Mm-hmm.
is that after that there exists a large n
Right.
such that,
From some point onward, you're within an epsilon.
right,
That's fine, but maybe I'm within epsilon over 2, epsilon over 4, epsilon over 8, epsilon over 3. And maybe I go backwards a little bit. Just like the sequence I gave you with the 1/2, the 1/3, the 1/4. You're still approaching 0, but every now and then you have a little hiccup, you go back for a little bit, you realize, oops, I'm going the wrong direction, and quickly correct and go forward again. It's possible that you might, at some point, get a little bit worse, and then you get better again. Then you get a little bit worse, and then you get better again. And the net effect is you get better more than you get worse. So at the end of the day, you do converge to the correct value. But you don't necessarily converge in the direction you want to go.
so the question is, does this become a problem given an epsilon? That is,
Well, in the Riemann sums case, in this case, we're always going to be fine. You give me an epsilon, I can always take a partition such that from some point onward, no matter what partition I take, as long as I have at least that many pieces, I'll be within epsilon.
right.
Over here, I can always take it so that my trig polynomial will always be within a certain approximation. What I can't assume is that I'm going in a strict direction. And again, this is why I've chosen today to labor on this point and not on the algebra. I am assuming you can read well enough to read a math book. I had Cameron and Kayla trying to read the math book this morning at breakfast. They were having some issues. So, but I think you've all gone far enough along that I think you can read this and you can go through the details of the proof. But I want you to see why we have to argue the way we do, why we have to be careful. There's a lot of natural tendencies you have in problems like this. And the difficulty is some of them are justifiable, but only with an enormous amount of work, and some of them are false. And so as a really good exercise, come up with a function where the lowest sum does not get better for some partition. And so you want to kind of think about where points are going. Can you do that? Or maybe there is a theorem in calculus that the lowest sums are always increasing and the upper sums are always decreasing. And it may just be the case that the proof is a pain. And that's why we don't do it in Calc 1 and Calc 2, because the students hate proofs enough already. Why make them see something like this? But think about that. Try to think, can you come up with a function where when you take this refinement, the lowest sum actually goes down? This is why, I'm sorry, where you take a new partition and the lower sum goes down. This is why the refinement is so much better when you do things dyadically, because then you're contained, you have this beautiful sequence. All right, so the idea of the proof now is we have these beautiful functions. We can approximate them with trig polynomials. And what we get is the following. So we have, 1 over j is our epsilon. We can choose a1j of x less than equal to chi ab of x less than equal to a2j of x. So that's not so bad. I mean, that's essentially just by definition. But we also want them to be close. And so we don't want them to differ by more than epsilon in, say, the regions we care about. So we can control how close our approximation is from A to B. Can A1j always be within epsilon of chi AB?
According to Fate, yes. Asked.
Yes.
At least if we pick an epsilon less than a half, we're going to have some point in the middle where it's not close enough to 0 or 1, and chi is always 0.
So chi is always 0 or 1. These functions a1j, a2j, as we get near the extremes, they differ from the value of our function by a lot. Here my function is equal to 0, but I'm essentially almost 1. So a1j and a2j can be quite far away from the characteristic function, but they're going to be far away on a very small set. We now look at trig polynomials. We can get a trig polynomial approximating this. Let's call it maybe t1j of x. And we can call this t2j of x. So these are finite trig polynomials. And we'll have minus m less than equal to m less than equal to m. I can choose this to be within epsilon of a1j. I can choose this to be within epsilon. Well, to be safe, I'm not going to choose it to be within epsilon. I'll choose it to be within epsilon over 2, epsilon over 4. Put in some fudge factor. So within epsilon over 2. Within epsilon over 2. So this is within epsilon over 2 of this. Well, this is exactly equal to this, except for a set of very small measure. So what we get is these and these are within epsilon. Actually, they will be within epsilon over 2, but they'll be within epsilon of each other, except on a very small set. Okay. So sort of like a sideways heart. Okay? They will be very close to each other. This really does a great job approximating this. This does a great job approximating this, so this will do a great job approximating this. What we're doing is we're passing our approximations. So we start off with a discontinuous function. We replace it with a continuous function at a small cost. We replace that with a finite trig polynomial at a small cost. A finite amount of small costs is still a small cost. Okay? And that's the whole point. Now we have these trig polynomials. And so now maybe t1j of x is the sum, m goes from minus m to m of bm e to the 2 pi I mx. And this is where it would be nice to have like 5 more minutes. All right. So now when we look at what goes on, we want to look at the limit as n goes to infinity, 1 over 2n plus 1, the sum n goes from minus n to n of chi ab of xn. Well, instead of using chi AB, we can use A1j with a very small error. Is that the case? Can I just replace chi AB with A1j and say, hey, look, A1j is close. So I see one, good. Why can't I do that? Well, not just that, but the errors might not be small. Remember, if I move over just a little bit, chi AB would be 0, but this could be very close to 1. Imagine my sequence is all points that are just a shade smaller than A, or just a shade larger than B. In that case, the error is enormous. But what we can do is we can sandwich this. This will be less than or equal to this with A2j. It'll be greater than or equal to A1j. So in particular, it'll be less than or equal to the limit as n goes to infinity, 1 over 2n plus 1, the sum n goes from minus n to n of A2j xn. That we can do, and we would get a similar bound in the other direction. And then we just show the upper and the lower bounds converge to the same thing, and we're done. Okay, so now that we have this, can we replace A2j with T2j with small error? That we can do because T2j is within epsilon over 2. Even though I do it a huge number of times, I then divide by that. So I can replace this A with a T plus something at most epsilon. It's actually epsilon over 2 in this case, but I can do something like that. And so if I do that, it's not going to be a problem. And now we need to just evaluate this sum. And now we have an exponential sum. So this over here is going to be the sum, n goes from minus n to n. I'm going to switch the order of summations. The sum m goes from minus m to big M. I'll put out the bm over here, and I'll have an e to the 2 pi I m, and then xn is n alpha. We don't have to worry about the mod 1. And now this is just the geometric series. If m equals 0, we get 1 every single time. We get 2n plus 1, we divide by 2n plus 1. If m does not equal 0, it's a geometric series and you can show that it's small. So at this point, unfortunately, we're out of time. Another 5 minutes would have been wonderful. If people want, I'm happy to talk a little bit more about this at the start of class on Wednesday. But this is the main idea behind what's going on. This is the level of approximations. This is how we approach the problems. Okay.